Okay, for our topic for this week is dynamics. And we're going to take a step beyond elementary dynamics, where forces are typically constant. And we're going to look at forces that depend on time, on position, and on velocity. Let's start with time-dependent forces. Because acceleration is dv dt, if we cross-multiply that, we see that acceleration times time is dv, which is an infinitesimally small velocity change. So we're going to integrate. This side will be a velocity integral from an initial to a final velocity. This side will be a time integral from an initial time to a final time. Now, the integral of dv is very easy to do. It's just going to be v, and then you've got to put in the upper and lower limits and subtract. So this side's the velocity change, and we see that's going to equal the integral of the acceleration. So we're going to put our time-dependent acceleration in here and use calculus to integrate it. Here's an example. A toy rocket's got a thrust force from a little chemical engine, and then there's a weight force opposing that. So we apply Newton's second law. Sum of the forces equals ma. Let's set up our axis this way. So that'll equal the thrust force minus the weight. So I could solve for the acceleration. Just divide through by mass. It'll be force over mass minus g. Here's an expression for the force. And the mass is 200 grams, so that's 0.2. So it's 3 plus 4t e to the minus 0.1t squared. All of that divided by 0.2, all of that minus g. Now dividing by 2 is like multiplying by 5. So that's 15 plus 20t e to the minus 0.1t squared, subtract g. So that's our acceleration as a function of time. So we're going to take that and substitute it into here and then integrate it because it builds character. So our initial time is 0. So we're just integrating 15. Well, I guess we can pair that with the minus g because that's a pretty easy integral to do. And then we'll have to work a little harder on this one. We can pull the 20 out in front, of course, because that's a constant. And then it's e to the minus 0.1t squared times t. The t was there. The 20's gone out in front. And all of that will be dt. And, of course, that's this side of the equation. All of that's just going to equal the velocity minus the initial velocity, which is 0. So this integral is just dead easy. This is just 15 minus g times t minus the lower limit of 0, or just 15 minus g times t. This side we're going to have to work a little bit more. But really, it's set up for an e to the u du, because if you call this thing u, then its derivative is minus 0.2t. So I'll just put a minus 0.2 here to set up the e to the u du, and then out in front, I'll just divide by minus 0.2, just to balance the expression and make sure it's still equal to what we had before. So now this is now e to the u du, and the integral of e to the u du is just itself. And then 20 divided by minus 0.2 is minus 100. So there we are. Okay, so this is now e to the u du, so it's e to the minus 0.1t squared. We still have to put in the upper and lower limits. Let's be clever, and we'll take this minus sign and use it to reverse these two limits. So the first thing I actually plug in is 0. So plugging in 0, e to the 0 is a 1. And then t, we substitute in with a minus sign for subtraction, e to the minus 0.1t squared. All of that equals v, and then of course we still have this here, 15 minus g multiplied by t. So that's an expression for the velocity as a function of time. Now, because 15 is bigger than g, this function is going to increase with time. This one is going to start off small, but is also going to increase with time. So this is like the chemical propulsion. Because if you put in times 0, we see that this term's initially 0. It'll be 1 minus 1. But then as time goes on, you're doing e to the minus a big number, which tends to 0. And so you get 1 minus 0. So you're getting a little bit of boost here from the chemical propulsion system. So anyway, so when you have a time-dependent force, find the time-dependent acceleration and then integrate it with respect to time. Okay, here's another time-dependent problem. This is rocket propulsion. and we're going to have a rocket that uses fuel at a constant rate. So here's a diagram of the rocket and a little bit of fuel at time t. So now the rocket mass you see is changing with time as we use up fuel. Now that means that the mass is going to decrease with time. Let's say m0 is the initial mass of rocket and fuel together. If you're using a constant rate r of fuel, then the mass will decrease in direct proportion to time, as follows. So now here's a picture of rocket plus a little bit of fuel that we're about to burn, both moving at speed v. Now what happens is the fuel gets ejected backwards, the burnt fuel gets ejected backwards at a rate u relative to the ship. Well, that means that it's slowed down by an amount u relative to the ground. It's now moving at speed v minus u. As a result of ejecting that fuel backwards, slowing it down relative to the ground, the rocket itself is now sped up a little bit by a tiny amount dv. So this is a closed system. The rocket and fuel are just pushing on each other. So it must be that momentum is conserved. So those two masses are moving together at speed v before the fuel is burned. After the fuel is burned, you've got the little bit of fuel that's slowed down, and then you've got the rocket that's increased a little bit in speed. Okay, so we expand the brackets and a bunch of stuff cancels. The mv term cancels, the dmv cancels, and you end up with 0 is minus u dm plus big M dv. So we're going to divide by dt and then bring this little term over to the other side. And what that's going to give me is big M dv dt is minus u dm dt. Now we need to interpret a little bit here, because little dm, remember, was that little bit of fuel that was ejected. So little dm dt, well, that's just the rate of fuel use. So that's a constant r. Okay? And little u is also a constant. That's the rate at which fuel travels relative to the ship. Now big M, we have to remember, though, is not a constant. It's actually time dependent. So you have constants on this side, but not on the other side. So let's substitute in the time dependency there and have a look at the differential equation that results. Okay, we're going to separate variables. Anything with a t in it, we'll bring it over here. So we'll cross-multiply up the dt and cross-multiply down the m naught term. The variables are now separated. We can now integrate, and at time 0 up to time t, we'll assume that the initial speed was 0, and we're integrating up to some final speed v. The dv integral is really easy to do. The integral of dv is just v, and we take the upper limit and subtract the lower limit. On this side, we got to do a little bit of work. Let's actually pull the minus sign in here, and then divide out in front. Oh, actually pull the minus r in. That would be better. Let's erase that. So I'll pull the minus r into the integral, and this is just going to set up a nice du over u situation. Because if we call this u, then its derivative is minus r dt. So this is d, or let's call it dv over v, because I don't want to confuse it with this u. And the integral of dv over v is just ln v. So this is mu times the ln of this thing, but then don't forget we've got to substitute in the limits, right? Now with logs, the way it works is if you do log a minus log b, it ends up being log of a over b. So it ends up being the log with the upper limit divided by the log with the lower limit. So this is an expression for the velocity of the rocket as a function of time. It depends on the fuel exhaust speed and it depends on the rate at which fuel is used. It's like a log of negative x graph. So it basically ends up looking like velocity, time. It ends up with some sort of decrease or increase like this. So that's another example of time-dependent dynamics. Now the next problem we're going to look at is forces that depend on position. Now the best example of a position-dependent force is a spring. And let's do this nasty example here. So we've got a spring, and it's going to, because it's stretched, it's going to pull this little collar, and it's going to pull the little collar in this direction because the little collar slides along this smooth rod. And it's a smooth rod, so there's no friction. So we're going to analyze the forces that act on this collar. You know, there'll be a normal force of some kind, and then there'll be a spring force, and then there'll be a weight. Now, we're not going to be so much interested in the y forces because there's a constraint there. The rod is just going to ensure that it moves horizontally. So we're going to be interested in the x forces. So this is the force from the spring. And the force from the spring is always k times an extension s. This, by the way, we'll call the x direction. We're going to find the net force in that direction. Now s, the extension of the spring, is going to be its length in this position minus its rest length of 3. Now, that force clearly acts on an angle. We're also going to want to know what that angle is. So sum of the forces is ma. A will be sum of the forces over the mass. And so the net x force is going to be ks cos theta divided by the mass. Now we know the mass is 2 kilograms. We know the elastic constant of the spring is 120. But let's just leave them as symbols for now. Okay. So first of all, as I was saying, s is the spring extension. It's the actual length minus the rest length. Now, the actual length is just this hypotenuse right here. So this is 4, this is x, because x is a variable. So the hypotenuse is the root of 16 plus x squared. Now, the rest length of the spring was given as 3. So that's an expression for s. So our acceleration is k over m times s, which is this thing, and then times cos theta. Well, cos theta, if we go back to our diagram, is going to be x over that same hypotenuse, because it's adjacent over hypotenuse. So that's going to be x over the root of 16 plus x squared. I guess I had some room over here, so let's put that in here. Okay, so that's our acceleration. It clearly depends on the position x. If we expand the bracket there, you get k over m times x, because that cancels. And then minus 3 k over mx over the root of 16 plus x squared. So this is a position-dependent acceleration. Now, the way that we're going to deal with that, because acceleration is dvt and v is ds dt, if I do a times ds dt, that's like dv dt times s. Times v. Because acceleration is dv dt and ds dt is v. So if I cancel the dt's, I get a ds is v dv. And if it's one dimension, I can take ds and I can replace it with dx. So I'm going to take my position-dependent acceleration and put it in here. It depends on x. I'll have to integrate with respect to x. This side I'm again integrating with respect to velocity, but that's a really easy integral to do. It's v to the 1 dv. That's just going to be v squared over 2 from the initial value to the final value. So this side's trivial. This side will have to work a little bit. So let us take that and pop it in there. Need a little bit more room. Alright, so it is going to be the integral of k over mx, and we'll split this up into two because there's two terms there, dx minus 3k over m. I'll save myself a step and pull the constant out, x, and then I'm going to write this 1 over square root as a negative exponent, negative 1/2 dx. And this is just going to be v squared over 2, and it's going to be from initial to final. Now this is a very easy integral to do. K over m is a constant, and the integral of x is just x squared over 2 from initial to final. This looks nasty, but if you call this v, then its derivative will just be 2x. So I can fudge that by putting a 2 here, and then balancing it by dividing by 2 out in front. And now I've got v to the minus 1/2 dv. And the integral of v to the minus 1/2 dv is v to the half over half, or 2 v to the half, or just 2 root v. So, putting that all together, k over m, this is x squared over 2 from initial to final. This is minus 3k over 2m, and it's going to be times 2 times 16 plus x squared. And again, that's going to be from initial to final. And that equals v squared over 2 from initial to final. Now, the initial x value you were given was 4, and the initial velocity was, I believe, starts at rest at 4. So this is k over m, k over 2m, and this is final was 1, initial is 2. This is 3k over m. So final is 1. Oh, I forgot the half there because it should be 2v to the half. I canceled the 2 there. That's why the 2's disappeared. And now, so now when I put in 1, I get root of 17. And then I put in the 4, and it's root 32. And then here it starts off at rest, and then the final speed's an unknown. Okay, now, the good news about that is that there's a much simpler way of doing it. Because when you integrate a position-dependent acceleration, when you have a position-dependent force, that means there's always a potential energy term. And it turns out that you know what the potential energy is. It's just half kx squared. It's just the spring force. So if we were to do this using energy, we'd say at the beginning it's at rest and there's only elastic energy, half kx squared. At the end, it's going to have, at this location, some kinetic energy, but there's still a spring stretch, so there's still some elastic energy. So the very simple energy equation says half kx squared at the beginning, that's initial x, is half kx squared at the end, that's final, plus half mv squared. Now the initial stretch is, with this thing starting off at 4, it's 4 squared plus 4 squared, it's root 32, minus the rest length of 3. And then the final stretch with it in here at 1, it's 4 squared plus 1 squared, it's root 17 minus 3. So you put those values in and you end up with this expression here. And that could very easily be solved for the final speed of v. Now the interesting thing is that that equation is identical, with a little bit of rearranging, to the answer that we found here. Okay? So there's the root 17, there's the root 4 over 2. This is ends up being like a half kx squared, because by the time you cross multiply the mass over here to this side to make it like mv squared over 2, this just looks like a half kx squared. With this mass disappeared here, those are just related to the actual extension values. So both of these together are just the change in the elastic energy, and that equals the kinetic energy. So you can, if you want, integrate the position-dependent acceleration, or the easier way to do it is just to use a potential energy function. So at this stage of the game, we've done a couple of problems with time-dependent dynamics, and we've also done one now with position-dependent dynamics. We're going to finish up with a couple where we have speed-dependent dynamics. Best example of that is the drag force, because with the drag force, your forces depend on the speed you're moving. Now, we can have a drag force that varies directly with the speed. That tends to be the case when you're not moving that quickly and you're moving in a thicker liquid, so a ball traveling in oil, or a very, very slow object moving through the air. If you tend to be going faster and through a less viscous liquid, like say a car traveling through the air, drag force tends to be quadratic at speed. It varies with the square of the speed. And the coefficients can actually be solved for if you have a sphere with linear drag, so say a ball bearing falling through oil. The drag coefficient actually ends up depending on the radius of the particle and on the viscosity of the liquid. Okay, this equation here for a sphere, linear drag for a sphere, is known as Stokes' law. It's one of Stokes' laws. For the other case, for quadratic drag, this coefficient here ends up being a half times something known as a drag coefficient times the density of the fluid, say the density of air if you're traveling through air, and multiplied by the cross-sectional area of the object. So typical example, a particle moving at 2.5 meters per second through heavy oil. It experiences a linear drag force of this much magnitude. So we imagine the particle, it's moving, okay, and there's going to be a drag force that's going to be tending to slow it down. So when we use sum of the forces is ma, the force is just this drag force, and that's going to equal ma. Now, the drag force depends on speed. So this is 0.01 v is ma. And just in terms of its direction, it's directed to the left. It's going to be slowing the object down. To solve this equation, we're going to write acceleration as dv dt, and then we're going to separate variables. So we're going to cross multiply the time upwards, and then divide by the mass. And then the dv is going to stay there, and we're going to cross multiply the v downwards. So we get this relationship here. Now that we're going to integrate from an initial speed to a final speed on that side, from an initial time to a final time on this side. Now this is dv over v, so that's ln v. And then you've got to go from the initial to the final value. So it'll be ln v minus ln v naught, which is the ln of v over v naught, if you remember that mathematical trick. This is a very easy integral. It's just minus 0.01 over the mass times time. Now the initial time is just 0, so by the time you put in time and 0, the 0 doesn't contribute anything, so you just end up with minus 0.01 t over the mass. And that equals the ln of v over v naught. Now, we're going to use an inverse function here. We're going to exponentiate both sides, so e is going to undo ln. So we'll put e to this side and e to this side. And so this side will just be v over v naught. And this side is just going to be e to the minus 0.01 over mass times time. So you cross multiply the v naught, and then you've got an expression with the velocity as a function of time. So this is how we're going to deal with velocity-dependent forces. We're going to apply Newton's second law, put in dv dt for acceleration, and then separate the variables. So we were given the initial velocity was 2.5, and that the mass is 0.3 kilograms, so those could be substituted in, and then you have a full function in terms of time. Okay, for a quadratic drag, let's look at a ball that's falling through the air. So quadratic drag means that the drag force varies with the square of speed. Now you can look back and see the drag force is 1/2 times the drag coefficient times the density of the medium, which is air, times the cross-sectional area, times the square of the speed. Now the drag coefficient, you could just look it up in a chart. For a ball, it's 0.47, so almost a half. Rho is the density of air, that's 1.29 kilograms per cubic meter. The cross-sectional area for a sphere is going to be a circle. It's going to be pi r squared. And then multiply by the square of the speed. So there's an expression for the drag force. Okay? That's the amount of drag on the particle. Now, it is falling, so there'll be a force mg. And then opposing that will be this drag force. So if we write Newton's second law, then we're suggested to use a y-axis that's downwards. Okay, sum of the forces is ma. So we're going to have mg minus the drag force equals ma. So we're going to have an acceleration that is g minus the drag force over m. So that's going to be cd rho pi r squared all over 2m v squared. Or if you like, it's g minus some constant times v squared. So that's an expression for the acceleration. So now, if we want to solve for the velocity as a function of time, what we just said was we have to put for acceleration dv dt, and then we have to separate the variables. So this is velocity dependent, so it's got to come down. And then the dt goes up. And then we're going to integrate from an initial time, which is 0, to a final time, and integrate, this is a velocity integral, from an initial velocity, which is 0, up to final velocity v. Now this is a trivial integral, this is just t, but we really have to work fairly hard on the left-hand side here to integrate this. Now, I think I just want us to set it up. Yeah, set up the integral to find v of t, evaluate if possible. Well, it's not really that hard. It's like 1 over 1 minus v squared. You can do a trigonometric substitution here. You can let v be like sine squared, sine, so it would be like g over k sine theta. Then you'll get like 1 minus sine squared here, which is cos squared, and you could proceed with doing a trig integral. Or probably an easier way is just to use the method of partial fractions, and then realize that this is almost like a difference of squares. It really is a difference of squares. And this is just a bit of a math challenge for you. So this is what we've got. And then we just want to solve for the constants a and b. And then once we've got the constants a and b, this is the technique of partial fractions. Once you've got the constants a and b, these two integrals are both trivial because they're just log integrals. Right? It's like 1 over b and 1 over v. So it's very easy to integrate those. So you can try, just as a little math challenge, and actually work out this integral. Then you'll have two log functions added together, and you can use the log property to simplify that. And then you can just invert that to actually get an expression solving for velocity as a function of time. So if you're interested, the partial fractions decomposition, the value of a and b end up being the same. So you substitute those, split it up into two integrals. You pull out the 1 over 2 root g. Then you need an extra minus root k here. So you divide by 1 over root k, and that sets up a du over u. Same thing here, pull out the 1 over 2 root g, factor it out in front, add the root k that you need, divide by root k in front, and you get this. So now it ends up being 1 over 2 root gk, and then this line is going to have a minus term, so it's going to end up in the denominator. This one doesn't have that minus. Well, or the coefficient's positive. There is a minus in the argument. And so we end up with this expression here. Oh, sorry, that one is plus, because it was plus there. So it's still plus there. So it's still plus there. This is the one because of this negative that ends up in the denominator. And now all of that, of course, equals the stuff on the other side, the very nice integral that was just t here. Okay. And so now we want to solve this for velocity as a function of time. Well, that's a little algebra challenge. You're going to cross multiply this part, obviously. And you're going to exponentiate both sides. And you now just want to solve this for velocity. Now you're going to have to cross multiply, gather like terms, factor, and then divide. But eventually you can solve for velocity as a function of time here.